Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden engineering of hand-weaving looms. We're going to dive into 3 core designs to solve a puzzle that has, well, let's just say it's frustrated weavers for generations. So, let's start with this really common and honestly pretty frustrating mystery. You've spent hours setting up your loom, you're following a pattern to the letter, and you start weaving, only to realize the design is showing up on the bottom of the fabric, where you can't even see it. What is going on?
You know, as weaver Janet Dawson asks here, this isn't just a simple mistake. It's actually a clue. It points to a really fundamental difference in how various looms are designed to work. It's like a mechanical language barrier, and today, we're gonna get fluent.
Okay, so here's the plan. To solve this whole thing, we're going to investigate the 3 main types of floor looms: the jack, the counterbalance, and the countermarch. We'll see how their mechanics really shape the final cloth. The absolute key to solving our upside-down mystery, and really to understanding looms in general, comes down to one single concept: the shed. So the shed is that essential opening, right? It's this little temporary tunnel that the shuttle flies through. Every loom makes one, but how it makes it, well, that changes absolutely everything about the process and what you end up with. And here it is. This is the heart of the matter. Looms create that opening in one of 2 ways. You've got a rising shed loom, which lifts the top threads up, and you have a sinking shed loom, which pulls the bottom threads down. Our whole upside-down mystery happens when there's a mismatch, when a pattern written for a sinking loom gets used on a rising one. All right, let's start with probably the most common type of loom out there, the jack loom. It's a classic example of a rising shed system. Just think of a car jack. It really only moves things in one direction, up. When you press a treadle, a little mechanism called a jack literally pushes specific shafts upwards. And what about the other shafts? Well, they just sit there, held down by gravity. Now, the trade-off here is super important. Jack looms are really popular because, hey, they're simple to set up, but that simplicity has a cost. Since only the top threads are actively lifted while the bottom ones are just kind of hanging out, the tension is uneven. For a delicate scarf, that's probably fine. But if you're making a tightly woven rug that needs a hard, even beat, this can be a huge problem. And this difference isn't just theoretical. You can actually hear it. Jack looms often use these heavy metal heddles that have to fall back down with a clank. And as one weaver points out, that can make them incredibly loud compared to other systems that are much quieter. So that main drawback of the jack loom, that uneven tension, it leads us directly to our next loom design, which tackles the problem in a totally different way. Okay, next up is the counterbalance loom. This is a much older and you could even say a more elegant solution to that whole tension problem. The way this works is just like a seesaw. The shafts are paired up over these pulleys or rollers, so when you press a treadle and pull one shaft down, its partner automatically gets pulled up. This means the threads are actively moving both up and down from the center line. It's a beautifully simple system. So, this loom's greatest strength is its balance. That perfectly even tension is fantastic for rugs or other dense fabrics that need a powerful, clean beat. But that reliance on balance is also its biggest weakness. It loves to lift 2 shafts and sink 2 shafts. If you ask it to do something unbalanced, like lift 3 and sink only 1, the whole seesaw mechanism kind of struggles, and you can end up with a messy, unclear opening for your shuttle. But what if you need that perfect tension for any pattern, balanced or not? Well, that brings us to the mastermind of the loom world, the countermarch. This thing is like a marionette puppet master. Instead of shafts being paired up, every single shaft is independently tied to both a rising action and a sinking action. So when you press a treadle, you're not just lifting some shafts. You are actively, simultaneously, pulling the others down. Nothing is left to chance. Nothing is passive. This dual action system is the source of all the countermarch's power, but it's also its biggest headache. You have to tie up everything twice. For every single treadle, you have to connect cords to make some shafts rise and then connect other cords to make the other shafts sink. If you forget to tie just one shaft, it won't move at all. It'll just hang there right in the middle, completely blocking your path. And this right here is the ultimate trade-off in loom design. Weavers are willing to spend hours, sometimes days, on a crazy complex setup because the payoff is absolute control.
A countermarch gives you a perfect, wide-open shed and flawless tension, no matter if you're lifting 1 shaft or 7. Any pattern is possible.
Okay, so let's bring all this home. Now that we get the mechanics, we can finally solve our upside-down mystery.
And there it is. The answer was never about a mistake you made, it was a translation issue. A lot of the older pattern books were written for counterbalance looms, which are sinking shed looms. So if you use that pattern on a jack loom, a rising shed loom, it does exactly what it's told. It lifts the threads the pattern indicated. But the pattern meant for those threads to sink. Your fabric isn't wrong, it's just being woven face down. This chart really lays out the core trade-offs, doesn't it? You can see this clear progression. The jack loom, it's all about simplicity. The counterbalance, it's about getting great tension, but for balanced weaves. And the countermarch, that's about having absolute, total control, but you pay for it with complexity. Each one is the right tool for a different job. And what's so fascinating is that the machine's design is literally woven into the final fabric. An engineering choice made about pulleys and levers directly changes the tension on every single thread. And that tension, in turn, dictates the drape, the density, and even the durability of the cloth that you create. So in the end, what we've seen are 3 very different engineering solutions to the same basic problem: how to make an opening to pass a thread through. Each one opens up a completely different set of possibilities for the artist. It kind of leaves us with a final thought. The right tool doesn't just make the job easier, it fundamentally changes what you're even able to imagine and create.